Good. So this is Maestro V2, so I'm not going to go in depth with all the introductory stuff. Some overview, so new Maestro V2, and then, oh, this is an old agenda. Sorry about that. I'll just start then. So Maestro 2 is basically a framework for creating simulation specification and executing these specifications. So as you notice, I'm writing simulation and not co-simulation specifications, and it is because Maestro 2 is very capable of performing single FMU simulations. So the motivation behind it is that it has to be expressive. It has to be explicit what is going to be going on when you execute it, and it has to be extendable. So you have to be able to extend its behavior by plugins. So the goal is to be better at supporting research into co-simulation based on FMI, and we want to participate in industry-related activities similar to Maestro 1. So we still need the maturity, stability, all these sorts of things. So what is it? Well, it's expressed in a DSL that we call Maestro Base Language, or Mabel for short. So it consists of a lexer, a parser, a to-become type checker, and currently an interpreter of this language. So we have expansion of Mabel statements via plugins, which function in a sort of macro expansion kind of way. But we also have a different kind of plugins, which are called interpretation plugins or runtime plugins, which are basically where we can provide runtime capabilities that a plugin can do something runtime. So we also plan to introduce verification. Right now we have something going on with where Prasad is implementing next VDM check, and we have Simon is using some work from Claudio, where he's checking that he got the right. Sorry. Where he's checking that he got some sequence right using an implementation in Prolog by Claudio. So the process that we're looking at is that you have a UI, which we are supporting the INTO-CPS application interface, the good old one, and then you get an initial Mabel specification. Now this Mabel specification has some functions that are not expanded yet. So we go into this process that we call the expansion process, where we have many different expansion plugins. One could be an initialization plugin, for example, that Simon has made. Another could be a simulation loop plugin, fixed step, which Kenneth has made. Or we also have a CSV writer, a type converter expansion plugin that basically insert Mabel statements to convert from one time to another. And once all of this expansion has completed, we have what we call a fully expanded Mabel specification. And basically here it is ready to be executed. So you can see the dashed verification below. We are not there yet, but it is planned work to have this verification step where you verify this Mabel specification, and then you get a fully expanded and verified Mabel specification that is ready for execution. So during execution, and right now execution is basically interpreting this Mabel specification, similar to what is done in Overture. And this execution can have various runtime plugins. For example, we have a plugin that knows how to interpret FMI statements. So when the Mabel specification has a set real, then during execution, it uses a runtime plugin to actually carry out this set real action. And in the end, you get some very nice results, which can be either in a comma separated values file, or it can be via WebSockets to the old INTO-CPS app, and so forth. So this is basically the process in Mabel. Good. So the language, as you can see here, is relatively small, and we hope to keep it like that. Anything that is advanced in terms of the statements and expressions you need will have to go into a runtime plugin. We are not interested in creating another general purpose language. So here is a very brief example of what Mabel looks like, what a Mabel specification looks like. In the top, you can see something that says start time, which is just to indicate that we have a type called real, and we have identifiers and variables. The next one indicates that we have arrays, and this is using one of the runtime plugins, where you can actually use this to call a runtime plugin and have it perform actions on FMUs. Then you have external initialize. This will be converted into multiple Mabel statements. So this is what we call an expansion plugin. Next one, you have load, which just shows how to load a runtime plugin. Then we have instantiate, which shows how to invoke a function on a runtime plugin. We have while statements, and we have a do step, and we have basically how to write a row to a CSV file. So these are all things that could exist in a Maple specification. So if we look a bit more into expansion plugins, like I said before, we have this external initialize. So basically the top line here, if that is in a Maple specification, when it goes through expansion, it will be removed and replaced by all of the lines below and even more. So basically this generates a lot of statements corresponding to an initialization to be carried out in terms of an FMI code simulation. So as you can see, we have the classical, if you know FMI, setup experiment. You have some set real, you have enter initialization mode, and you have set real again, and you have exit initialization mode. So this is all regular FMI function calls to set up an FMI code simulation. And as you can see, it's very clear what is going to happen. So this is one of the things that we're aiming for, is that it has to be very explicit in terms of what's happening. So when people ask us, how do you do initialization, which master are going to be using all of this, and they have further questions, when are you setting this variable in this FMUs, then we can always just say, look at the specification. And we don't have to dig through the code ourselves and look at which branch it's going off into. So runtime plugin, here are the tools that I mentioned. We have the FMI2. And if you know the FMI standard, you can see that these instantiate and free instance are very similar to what it actually looks like in the FMI. You also have the FMI component, which are for an actual instance of an FMU. You have the setup experiment, do step, and so forth. So in terms of performance, so you should not compare the orange line, because the COE does a lot of checking every time it's running a step in the code simulation. So this is not really fair to compare this. So we should compare the green line and the blue line. And what this shows is that the lower is better, because it's the time it takes to execute a code simulation. So if you look on the x-axis, then you have 0, which means that you are running a simulation with an end time of 0. So of course it's not there. But if you have 1, then you're running a simulation with an end time of 1. And this goes on until you're running a simulation with an end time of 100 in the end. So basically here we are running 100 code simulations with different end times from 1 to 100. And the blue line is the new approach, whereas the green line is the old approach. So you can see that the performance now is much better. Now, another interesting thing is that if you look at what we have here, this is quite close to a C implementation, or how to invoke these FMI functions in C. And this is what we are going to do in the future, is that we would like to try and code generate this to either C, C++, or Rust. We don't know yet, but we expect that this will give us even more performance squeezed out of this. So it is going to be relatively close to this, and the advanced stuff will have to exist in plugins, either expansion plugins or interpreter plugins. So the status is that currently we have an initialization expansion plugin, a fixed step expansion plugin. We have a type converter expansion plugin that I forgot in this list. Then for runtime plugins, we have a CSV file, we have WebSocket, we have FMI. In terms of documentation, we are following Christian's great idea of converting all of the INTO-CPS documentation for read the docs, and we are progressing on that. Verification, well, Nick is doing some with VDM check. Kenneth has done some initial stuff on verifying that whenever we load an FMU, it's unloaded again. So now we just have the big things that we need is maturity, some more structure, better documentation, and we need more basic features. So everyone who's interested can be involved in this. We have a lot of separated actions that can be taken. And I think, and we welcome Prasad to the team, who's joined us recently and done some great work on documentation for now. So feel free to ask some questions.